Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Terima kasih kepada rekan-rekan civil engineer seluruh Indonesia yang join di acara webinar Testindo Bridge Load Testing, Evaluating Load Testing for Bridge. Hari ini hari berbahagia, alhamdulillah, puji syukur kepada Allah Subhanahu Wa Taala, beriring salawat dan salam bagi baginda Nabi Muhammad SAW. Hari berbahagia ini hari Rabu 17 Maret 2021 kita berkumpul di suasana pandemi ini untuk sharing session, dan acara kita pagi ini adalah webinar Bridge Load Testing. Jadi evaluating load testing, kita lebih banyak kepada bridge, tapi load testing dalam artian ini adalah struktur secara umum mirip gitu ya. Dan pembicara kita adalah pembicara utama kita, Mr. Jess Grimson. Beliau ini setelah saya sampaikan juga di introduction webinar kita, beliau adalah salah satu anggota Standing Committee on Testing and Evaluation of Transportation Structure di Amerika. Oke, acara kita hari ini saya hanya membuka dan mendampingi Bapak Ibu sampai akhir membuka. Jadi kita ada dua sesi. Pertama pembukaan dari Pak Iwan Zarkasi, orang tua kita. Alhamdulillah beliau masih aktif dan bersemangat. Pagi ini beliau akan memberikan opening speech mengenai acara ini dalam bahasa Indonesia. Apa-apa yang kita bahasa Indonesia kita biasakan. Lalu sesi kedua, Mr. Jess Grimson akan menyampaikan materinya. Perlu saya sampaikan bahwa sesi webinar ini semua peserta kita mute, dan pertanyaan disampaikan melalui kolom question. Ada kolom question kalau Bapak Ibu ada nanti problem dengan pemakaian kolom question, bisa nanti texting, chat ke saya atau chat ke WhatsApp saya. Nanti saya akan bantu, dan nanti akan saya berikan sesi untuk mungkin ada yang pengen bicara langsung ya, nanti silakan kontak saya yang punya pertanyaan yang betul-betul spesifik dan penting rasanya untuk dijawab oleh narasumber utama kita, Mr. Jess. Nanti silakan kontak saya secara japri di jalur WhatsApp atau di jalur jalur go to webinar ini ada kolom chat. Nanti saya akan berikan kesempatan untuk bertanya langsung ke Mr. Jess. Oke, kita tidak berpanjang lebar. Kita masuk ke acara yang utama, pembukaan dari Pak Iwan Zarkasi. Kepada waktu dan tempat saya persilahkan ke Pak Iwan.
Terima kasih kepada Pak Zul yang memberi kesempatan kepada saya, Iwan Zarkasi, untuk memberikan opening speech pada acara webinar kali ini. Saya kira webinar kali ini sangat menarik karena terkait dengan structural loading test for evaluating structural performance, dengan case study adalah bridge test. Saya kira pekerjaan sekarang ini akan sangat terbantu dengan kehadiran apa disebut dengan sistem implementasi atau sistem sensor yang berkembang. PU dalam hal ini Bina Marga banyak kerjasama dengan BDI, karena pada waktu awal kita akuisisi alat dan sebagainya itu kita berkompeten dengan BDI sebagai penyedia alat untuk diagnostik jembatan. Dan saya kira kegiatan ini akan terus berkembang sesuai dengan perkembangan IT untuk evaluasi struktur. Kalau zaman dulu kita membayangkan untuk mengevaluasi struktur itu sangat rumit. Tapi dengan kehadiran alat sensor yang mulai dari sifatnya untuk displacement, regangan, dan lain sebagainya, itu bisa kita akuisasi datanya. Dengan memperoleh data tersebut, maka kita bisa mengetahui performance dari struktur tersebut. Kegiatan ini sangat penting saya kira mulai dari pelaksanaan itu kita juga sudah banyak menggunakan instrumentasi untuk mengetahui geometrinya dan tegangan-tegangannya. Demikian juga pada saat operasional sebelumnya untuk jembatan-jembatan khusus kita mewajibkan adanya layak fungsi. Nah, layak fungsi ini ibaratnya adalah menguji performa tersebut. Terlebih lagi untuk jembatan-jembatan yang sudah operasional dengan masa layan yang cukup, gitu, kita juga harus bisa mengevaluasi performa jembatan tersebut. Nah, biasanya untuk mengevaluasi performa tersebut menggunakan sistem instrumentasi atau IT ini. Sensor kita pasangkan musik dengan suatu beban. Sekarang ini sudah banyak sekali yang kita lakukan untuk statik maupun dinamis, tetapi juga nanti akan berkembang lagi dengan soal umur, performance, sebagainya. Saya kira kerjasama dengan pihak luar yang notabene sudah berkembang, ini sangat menguntungkan kita. Lagi pula dengan pandemi COVID sekarang ini, kita bisa langsung belajar dari BDI, dalam hal ini Mr. J. Grimson. Mr. Grimson, I'd like to express my thanks very much for your sharing knowledge in this morning. I think in USA is now in the night, right?
Yeah, that's correct, yes.
So we have different times around 12.
Yes.
As you know, Indonesia is located in the equator. We have also 3 time zone, from the eastern until to the western to eastern, 3
Yes.
time zone. And United States, I think you have also 3 time zone, right?
Yes.
So
4 time zones.
we actually, the big country, spread from this distance is nearly the same as London to the Ukraine. Many bridges and should be tested to the understanding to understand the performance. So we want to have more collaboration with you on the next occasion. I'd like to invite you to Indonesia and give some presentation.
Yes, I would like that.
Saya kira demikian Pak Zul. Pak Zul sebagai pionir bisa tetap kerjasama dengan pengembang alat dari banyak negara yang saya kira mereka sudah maju, sehingga kita bisa kerjasama sebagaimana kita mengetahui keandalan struktur ini. Saya kira ini yang bisa kami berikan, dan kami men-challenge kepada insinyur-insinyur Indonesia untuk belajar bagaimana mengintegrasikan antara pengetahuan yang sifatnya civil engineering dengan pengetahuan yang sifatnya ini boleh dikatakan adalah instrumentasi ini sangat penting ini, sehingga kita bisa mengembangkan ide, memahami karakter struktur yang sebenarnya. Demikian yang bisa kami sampaikan. Terima sekali lagi kami ucapkan terima kasih kepada Pak dan Pak J. Grimson untuk acara webinar ini. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Semoga sehat selalu Pak dan lancar dalam aktivitasnya Pak Iwan. Kita masuk ke acara utama kita, presentasi dari Mr. Jess Grimson. So please start your presentation, Jess.
Okay.
Thank you.
Well, first, thank you to everyone here for coming out and spending some time listening to me give a presentation about diagnostic load testing and structural health monitoring of bridges. I've been fortunate enough to visit Indonesia several times now and give some presentations locally and been involved with a few small projects in Indonesia. And I'm looking forward to hopefully getting back there very soon and give some more presentations and hopefully work with some of you as well. So I will share my screen here, and I think what I'll do is I'll turn off my video for now just so that we have a maximum bandwidth for presenting the presentation. And I think Zulfriqi had mentioned we will have questions in the chat box, and we'll try and address some questions maybe halfway through the presentation and then again near the end of the presentation.
But please, Pak Jis, speak slow and louder.
Yes, okay, I'll do my best.
Easy understanding. Yeah.
Okay, I'll do my best to
Louder and
slow.
Yeah.
So my presentation is about diagnostic testing and structural health monitoring for really all types of structures. The agenda for the presentation, I will talk a little bit about BDI, a little background in our company, and then I will talk about our sensors and instruments that we most typically use on these type of projects. Then I'll discuss diagnostic load testing specifically, as well as I have a case study to go over with regards to load testing. Then I'll talk a little bit about structural health monitoring. And finally, talk a little bit about data management, which I think is a very important component to any successful structural health monitoring program. So a little about BDI. BDI is a little over 30 years old as a company now. The company started as really a research project at the University of Colorado and was sponsored by Federal Highways along with State Department of Transportation. And the project involved developing a new method for collecting data from a bridge and coming up with a better way to analyze that bridge behavior using the data. After the project was successfully completed, the company was started in 1989, and the very first thing the company really engaged in was developing some structural testing hardware, sensors, and data acquisition, along with some finite element analysis software to use in conjunction with the data that we were collecting. We adapted both the hardware specifically for challenging field applications and developed the software so that it could be easily adapted to the data that was being collected. To date, we've tested or evaluated over 1,000 structures around the world. Of course, mostly in the US, but we have completed many projects overseas and worked with many partners around the world in doing so. What's unique about BDI is that we are an engineering firm really at the heart of it, as we also produce sensors and data acquisition, which is a pretty unique combination in this industry. A little about our locations. We have our headquarters in Colorado, near the center of the country. And we have a few offices that we've opened up around the country as well to sort of serve local projects and local regions. You guys are familiar with Indonesia. We have Testindo in Jakarta, who we work with to support local projects and instrumentation in the country of Indonesia. a little overview of BDI, and this is a little more complete picture of all the services and the equipment we offer. Ultimately, we are an instrumentation service company. We really provide two types of instrumentation service with regards to testing, and that's diagnostic testing and structural monitoring, the two things that I'll be talking a little more about today here. We offer analysis services, and that really is focused on the data that we collect. So we will add value to our projects by completing finite element analysis or maybe simplified data analysis for our clients. The other segment is instruments. We manufacture and produce sensors as well as data acquisition equipment. And then we add data management as well. So we can offer services of remote data collection, data management, data analytics, and web hosting of our data. Another area that we're not really covering in this presentation, but I think it's worth bringing up, is we have a full service non-destructive evaluation division within our company. So while we're talking more about instrumentation and structural monitoring, it's looking at the performance of the structure as a whole. We have a division that looks more at the material level properties of a structure. So looking at corrosion of concrete, steel, cracking in steel, or wire breaks and tendons, that type of data evaluation. Again, as I mentioned, kind of what makes BDI really unique is that we really are this engineering firm to start out with. Our staff consists of about 60 people now, and about 35 of those staff are all engineers and engineering technicians, most of them being civil structural engineers. And then we also manufacture our own equipment, and that equipment we manufacture is all derived from our experience in the field. So we've tried very hard to develop instruments and data acquisition that is very simple to use, very easy to deploy, and very reliable for the long term. So with that, I'll talk a little bit about our instruments. Again, as I mentioned, we really developed instruments focused on diagnostic testing, and as our company has grown, we've expanded this sensor line and data acquisition line to really cover both diagnostic testing as well as structural health monitoring. The first system is really what we developed as the beginning of the company. This was used to collect data under controlled diagnostic tests in the field. We're currently on our 4th generation of this hardware since we first developed it in 1989. And using the latest technology, again, coupled with very simple to use and very rugged, very easy to deploy in the field. The system really contains a few components when it comes to how it works. Typically, you'll see a group of sensors and data acquisition. In this case, we have 4-channel nodes and a group of sensors, and there will be many of these placed around the structure. We'll have a base station that will create the wireless network on site, and we'll have a load position indicator that we use for tracking the position of the truck on the bridge as we're conducting our test. And then we have an application where we would be controlling this hardware in real time while we conduct the test. What makes our system unique really centers around our IntelliDucer. This makes the system very easy to install. Every single sensor that we plug into the system self-identifies. So within this connector here, we have a memory chip, and it will contain all the information about the sensor, so that when we're in the field, we can plug it into any one of these nodes, any channel, and it will automatically identify itself. These nodes are wireless, battery powered, and weatherproof. So again, very easy to deploy. You can collect data for roughly 40 hours on one charge, which is typically more than enough time to conduct a diagnostic load test. And then we have a wireless base station. As I mentioned, this is what generates the wireless network on site for the nodes to connect to and your computer to connect to. And again, I mentioned the load position tracker. This is attached to the vehicle, and that gives us the longitudinal position of the vehicle on the bridge, which is really an important piece to how our system works. It allows us to look at all of the data that we collect with respect to the position of the load, rather than what people typically do is look at it in the time domain. And this is particularly important when we're looking at calibrating finite element models, because it's much easier to look at data with respect to a load position than it is in time. The next set of instrumentation we have is our structural monitoring system. This is a little bit more complicated in that we have a system that is intended to be deployed permanently or semi-permanently on a structure to collect data over some period of time, or maybe even the life of the structure. So this system contains a few main components, and I understand there's a lot of words on here, and we'll be sharing this presentation with everybody, so we'll give you a chance to download this after the webinar. But essentially, what we typically have is a central data logging system that will have our data logger, some sort of external communication method, could be a cellular modem, satellite modem, maybe a direct landline. We would have a battery backup system and then some source of power. Within there, we would have internal communication and power distribution. Then we would distribute the data acquisition system out to closer to where the sensors or group of sensors are located. So really what we call this is a distributed data acquisition system for larger scale monitoring applications. The other side is how we collect the data itself. We have applications to configure the system locally or remotely. We can push the data to a client server, or we can push it to our cloud and provide a hosted service, giving our clients the ability to log in wherever they are and manage the data that's being collected. The systems really break down into a few main components for us. We have data acquisition devices that again are distributed throughout the structure. We have our core data logger, which is the brains behind the structural monitoring system. It's what collects all of the data and processes all of that data into data files, and then would ship that data out off-site. And then the other component is really the power and communication of the system itself. And it's important to have a very robust power system as well as a robust and redundant communication system in a monitoring project. With regards to sensors, we produce really just a handful of sensors, which accounts for probably 80 to 90% of the sensors that we typically use on a structure. That's strain, acceleration or vibration, rotation, oh, sorry about that, and then also foil strain gauges when we need to measure strain at the surface of the steel or concrete, and then displacement sensors. And these are really the sort of the main sensors that we deploy out on a project. We can also deploy other devices as well, depending on what the project is looking for. A very typical system and sensor we would deploy is an acoustic emission sensor. And we use those for identifying cracks that might be occurring in steel or concrete. They're particularly used on cables and pre-stressing concrete where there's post-tension tendons. And we're concerned about the potential for wire breaks within those tendons themselves as these large cables age and maybe don't have the latest dehumidification systems or are sealed correctly. They tend to corrode, and as you get wire breaks, it's important to identify those, and acoustic emission can identify those. This is a typical, similar to the STS system, a distributed acoustic emission data acquisition system. And we can integrate this directly with our structural monitoring system. Other sensors that we've integrated that are common on many of the larger scale monitoring systems, vibrating wire sensors, the very typical sensor, and they produce many different types of sensors or types of measurements. Weather stations are very typical to include on large scale structures. We've included pressure gauges in some instances where we're looking at including a pressure cell, maybe at a bearing location. Load cells may be used in line, in some cases in cables or tendons. Common one that we've installed as well is weigh in motion. And this is important for being able to track the load that's being applied to the structure in real time. We can correlate the load to the response of the structure. Wind speed is another common measurement to take, especially on large scale cable stay or suspension bridges. Another system that we would integrate on different monitoring projects is GPS sensors and automated total stations. They can be used very effectively on some cases where we're looking at three-dimensional position of, say, a tower on a large cable stay bridge or suspension bridge. An automated total station will help to look at a deflection profile, again, of a large scale structure. So they're nice tools to be able to add to typical structural monitoring. Geotechnical instruments, of course, are also critical to include in some of the monitoring that we're doing at the outset of construction, looking at potential for settlement, interaction of soil with the abutments or piers, ground anchors in some cases we've installed, and of course groundwater elevation is always critical for looking at slope stability around a structure. Vibration sensors are also another common one, and I think probably used a fair bit in Indonesia, since there's a very highly active earthquake area in Indonesia, to be able to identify earthquakes and the peak ground acceleration as it correlates to the structural response is a very common measurement to include in a monitoring system. I mentioned a little bit about weigh in motion. Why it's really so important is we've used this for looking at fatigue cycles in structures, really to be able to look at the true live load impact that is being introduced on the structure itself. And overall, quite economical to install these weigh in motion systems now. There's a couple different varieties depending on the accuracy you're looking for, but work very well for looking at correlating load response to structural response. And even more important nowadays, when digital twin modeling is becoming much more prevalent in structural health monitoring. Wireless, of course, is another tool to deploy depending on the difficulty of being able to install a hardwired system. Being able to integrate different wireless technology with maybe more traditional structural health monitoring is really important to be able to keep a system more economical, and now works quite well. Even running on batteries for many years at a time now. So these are all the typical tools that we look to deploy on a monitoring system. When it comes to our software, again, we tried our hardest to develop a very effective tool and a powerful tool, yet keeping it very simple to use. So with everything being self-identifying, it's very easy to deploy a testing system or a monitoring system and immediately start collecting data. For data processing, we have a couple of applications we typically use. One of them is our STS View application, and that is used for loading the data files that we collect in the field and giving you and us the ability to review that data very quickly and look at many different sensor types as well as many different data files at the same time. It gives us the option to add filters to the data, essentially allowing some more refined data processing on the data that was collected. This is typically pretty important as we start refining that data and preparing the data for what we typically do, which is a finite element model analysis coupled with the data that we collect. Another tool that we developed is specifically for looking at cable force, in situ cable force. So for an example, a cable stay bridge where you're curious about what the force is in a stay cable, we can use an accelerometer and excite the cable, get the cable vibrating, and take that data, convert it to the frequency domain as shown in the slide here. This is over here is the raw data that was collected, and this is the frequency analysis, the frequency domain of the data. This application will allow us to enter the cable properties. With those cable properties, it can find the peak frequency mode and calculate the fundamental mode so that we can calculate the in situ force of the cable. we have quite a few projects where we're hired to go out and evaluate cables that are installed on various structures. And this is the application we use to do that. The other side of our application or software is really the data management for large-scale monitoring systems. And I think it's extremely important to have a tool that can represent and display the data in a meaningful way. Most owners of structures are not interested in looking at the raw data or all of the data being collected on a structure, but they're interested in what decisions need to be made on that structure, what maintenance decisions need to be made. So we tried to develop a application that will really help owners make real-time decisions on maintenance programs for their structure. Another important aspect to particularly structural health monitoring is the quality control of the data. How do we manage the quality of the data coming in, and how do we know that all of our systems are performing optimally? So we have systems that we've developed to manage our communication, manage the hard drives of our data logger, manage the power systems that are out on a given site, and give us warnings when things aren't looking like they're up to where they should be. So this is, again, an important part of being able to manage a structural monitoring system. So next, I'd like to talk a little bit about diagnostic load testing. This, again, as I mentioned earlier, is really how the company started, and still one of the main services that we offer as a company here in the US. Part of looking at conducting a diagnostic load test, we really need to identify whether a load test can meet the objectives. And I say that in first, we have to understand what problems are occurring with a structure and will a load test meet those objectives. Once we understand what the problem is, then we can select the type of load test to meet those objectives. Understanding the outcome of a load test, learning how to use this outcome to meet the objectives, as well as to evaluate the bridge structural behavior. Then we can determine the structural safety of a bridge, quantified by the probability of failure, and update with the information from a load test. So really, what is a load test? A diagnostic load test measures the true actual response of a structure against a known load, and that's for the purpose of developing a realistic analytical model. The load tests are often used to reduce uncertainties with respect to as-built conditions that may not be able to be analyzed through traditional methods. This is typically secondary effects, something like a guardrail, a sidewalk, what is the true transverse distribution, or potentially other secondary non-structural elements that may change the response. We typically use a maximum service load for the load test itself, and it is typically performed in a very short time frame with a low impact on traffic. The data that's collected is used to refine and validate an analytical approach. And that is typically a finite element analysis or finite element model of the structure. The final result is typically an updated load rating for the bridge with critical load rating locations. So as you can see in this picture here, this is the type of data that we're trying to evaluate. How heavy of a truck can safely cross that structure? Skip one here, sorry about that. Some of the key considerations, I mentioned this before, but number one, we really must have a clear definition of the objectives of the load test. Some typical reasons for load testing, field verification of design assumptions. So again, we have design assumptions of the structure and how those components react to load, and we may not understand that completely. Another big one is the true distribution of live load through the structure. It's often a fair bit different than how you would traditionally calculate the live load distribution. It might be for measuring stress responses in certain members, or determining the actual performance of different bridge components. It may be just focused directly on say a frozen bearing or a frozen pin. And then lastly, which is the more typical, is for developing the load rating for a particular vehicle configuration. One thing that's always important to look at is the cost benefit analysis before undertaking a load test. These numbers are typical average range in US dollars, but if we were to conduct a typical hand load rating calculation, the cost would range between $1,500 and $5,500. A typical diagnostic load test, this is what we would charge to go out and conduct a load test here, ranges between $25,000 and $35,000, but does not include access or traffic control. Typically, the access and traffic control is handled by the bridge owner. And then what are the alternatives? What has to happen if we don't conduct a test? There's potentially replacement of the structure, potentially strengthening or repairing, or load posting the structure, which may have economic impacts with having to reroute critical traffic. So really, it comes down to going through the exercise to calculate what that alternative is, and that's going to allow you to better understand the cost benefit. So I'm going to go through a case study here, a project that I was involved in Arizona. We were down there, and I think we ran load tests on about 6 or 7 different bridges. And in this case, this structure was a 4-span cast in place reinforced concrete slab, and it was a single lane bridge. So a relatively small local bridge that we ran the load test on. The current load rating limits were telling them that that typical load trucks, legal load trucks, were not allowed to cross the bridge. The condition of the bridge was actually in very good condition. Visually, no signs of real deterioration at all. So the objective in this test was to provide a more accurate load rating or load carrying capacity for the bridge through a diagnostic load test. We did a very simple cost benefit analysis. The state estimated that the strengthening to increase the load rating on the bridge was roughly $250,000 US dollars, and was going to involve some carbon fiber strengthening of the slab itself. The diagnostic load test for this project was roughly $30,000. So the first phase of any diagnostic load test is planning and execution. The first thing we do is develop instrumentation plans. And a structure like this, where we have 4 spans, we focused our instrumentation on 2 of the 4 spans and used the symmetry of the bridge to assume the responses would be the same in those other spans. Site planning, we had to develop access to the bridge and traffic control, and we had to hire a loading vehicle, in this case a dump truck with gravel. The next is we execute the diagnostic load test. We collect the data on site, and one of the more important portions is to really validate that data while we're on site. There's a lot of cost in going out and collecting the data. So we need to be sure that we are collecting good quality data. And again, that goes back to the software we've developed, giving the engineer on site the tools to evaluate that data and ensure that they're collecting good quality data. The other planning and execution, the instrumentation plan, again, I said it focused on 2 of 4 spans with 6 cross sections of sensors. We had 3 lateral load paths. We accessed the structure with scaffolding, and it was a local road, so we didn't have any traffic control. Data interpretation, the first thing that we do is we look at the quality of the data. We look at reproducibility and looking at data that starts at 0 and ends at 0. So we spend a good amount of time evaluating that data up front before we start getting into the analytical model. The next is to develop our analytical model. And as you can see here, what we do is we reproduce the field load test in our finite element analysis software. You can see sensors even in our finite element analysis. You can see the footprint of the truck. So we're reproducing that load test in our computer model. We then start adjusting the parameters of our model until we have a final field verified model. The results from our finite element analysis match the results from our field test. So again, we're looking at the quality of our data, reproducibility. Some of the modeling parameters, and again, I know there's a lot of words here and I don't expect everybody to read them all, but we have some basic parameters that we look at refining. Secondary members stiffness, bearing support conditions, modulus of concrete is a typical one for us to be adjusting. Member eccentricities, really the geometry of our model, and then connection stiffnesses. In the case of the bridge we tested, these were the model parameters that we developed for this bridge. It was a 2D model of shell and frame elements. We had a 2D footprint of the truck. We did loading increments every 2 feet. So we had 204 load cases. With the 36 gauges and 6 displacement, 6 rotation, we had 9,792 measurements to compare against for all those load conditions. So you can see it's a very refined process for analyzing and adjusting our model. What we adjusted were the stiffness of the supports, the slab stiffness in different regions of the bridge, because we had positive moment and negative moment regions that crack differently and create slightly different stiffness of concrete there. The end result, you can see the dots here overlying on our lines. You can see we had a very good correlation between the field data we collected and the analytical model output. We had minor adjustments to some of our parameters, and finally had a very high correlation coefficient between the measured response and the analytical data. And then finally, we apply our load rating formula within our model itself. We have potentially some adjustments to make in our model to reduce or to add some conservatism to the capacity. We still do have to calculate our capacities of the elements of the model based on geometry and member properties. We have to apply our dead load to the structure, and then we can extract those results. And finally, we can report. And it really is a very focused report that outlines the results and any recommendations. Typically, this involves an executive summary with purely the load rating results, a summary of our load testing procedure and instruments, what our analysis approach was for the project, and then any load rating recommendations. With a finite element model, we can really provide detailed load ratings for every component of the bridge itself. So it becomes a very powerful report if we're going to target any retrofit or construction work to strengthen the bridge itself. So moving on from diagnostic testing, we'll talk a little bit about structural health monitoring. So structural health monitoring, we usually get asked this why, and what are the reasons we need to execute a structural health monitoring program. Typically, it involves, looking at structural performance over a larger period of time, where a diagnostic test is really a snapshot of how the structure is performing at that time. When we want to look at the performance over a longer period of time and take into account some of the other variables other than pure live load response, like settlement or temperature-induced stresses, potentially it has to do with the construction of the bridge itself, and maybe for verifying new design techniques. Another reasons are for supporting inspections, looking at the performance of key components of a structure that are typically causing issues in the maintenance side. It allows the owners to keep a remote eye on the performance and particularly potential problems or specific problems within the bridge itself. We can look at road surface conditions, and we can look at weather and how that relates to the performance of the structure. And another reason is for digital twin calibration. This is, again, a sort of an emerging technology, but it's being used a lot more now, where we have a real-time finite element model of the bridge, and we're collecting long-term data and evaluating how that changes that model and what parameters are changing to sort of help guide maintenance funding for the structure, looking at what parts of the structure may not be performing well. Typical components for a structural health monitoring system. Bearing movement is always an important aspect, and bearing force itself. So looking at how bearings are performing on a structure and how much the structure is moving with respect to temperature. Expansion joint movement is another common one to look at how much expansion's moving. Cable forces, we often will include accelerometers or load cells to identify what the force is in a stay cable or a suspension cable. Looking at deck stresses and superstructure strains as well. These are some of the main components that make up a typical structural health monitoring system. Other data that we integrate, again, goes back to a little bit of what I talked about earlier. We can integrate the automated total stations, weigh in motion, of course, the high-speed data acquisition. We can integrate inspection reports on a structure, so we can have a system that really combines more than just sensor data on a bridge, but visual data can be added to this as well. We talked about acoustic emission, fiber optics can be added as needed. Cameras are a very typical add-on for a monitoring system, whether it's looking at live load traffic on the structure or potentially impacts on the structure itself. Suspender or cable behavior is a very, very common one. The cables are a extremely critical component to a large structure like that, and understanding how these cables are performing over time is a very difficult task. We can do this a couple different ways. One, through accelerometers or inline load cells to look at the force of the cable and how that might change over time. We can use acoustic emission to look at wire breaks within the tendon itself, and that gives us some indication of corrosion and rate of corrosion in the cables. And then we can look at the tower survey itself too. How much is the tower moving over time, giving an indication that maybe some cables are relaxing on one side of the tower. Fracture critical structures and fatigue monitoring is a very common monitoring method that we've executed many times, especially on older steel structures that are fracture critical. Mostly that involves strain at critical locations to look at what the stress levels are and principal stress direction at locations that are prone to fatigue or stress concentrations. Acoustic emission is also used to listen for the potential of cracking within steel. And then we've developed a sensor for looking at crack growth around critical locations or locations where cracks have formed, and we want to get a sense of how fast are those cracks propagating. Pier and tower movement is another very common one. So here's an example of some wireless sensors, wireless tilt sensors that are just purely looking at the rotation of a pier over time. This is an example of a GPS sensor that is placed on a pier of a bridge to give us three-dimensional movement of that pier. Is that pier moving down river? Is it settling down? It gives us a three-dimensional point of that pier movement. And here's an example of a automatic total station where we have a station that is secured at the abutment of a bridge and shooting over to prisms located at different locations of the bridge to get a sense of how much that is moving over time. Concrete cracking is another very common problem that is seen on various concrete, whether it's reinforced or post-tension bridges. We can go, of course, the traditional route of putting visual sensors on, but we still have the ability to put some lower speed crack sensors on, or even higher speed crack sensors if we think that the crack is propagating from live load, this gives us the ability to see how much that crack is opening and closing under live load events. One more common monitoring method that we've been deploying here, and I think probably would be useful in Indonesia as well, is looking at the potential for vessel or ship collisions on a structure. This is a big problem in the United States on navigable water. And so we've deployed systems that look at the bridge vibration and the pier vibration, and then have cameras to capture what vessel has collided in the bridge. And we can look at pre and post video of the vessel colliding with the structure. And in this case, the client was looking at identifying the vessel by their markings and ultimately going after their insurance to pay for repairs on the structure. I've mentioned acoustic emission a few times now. Mostly we're using it now on cables to look at wire breaks. But again, we can look at fracture critical structures. So you can see in this one picture here, this eye bar has cracked straight across. We're losing, of course, all of its load carrying capacity. And acoustic emission sensors can listen for this type of cracking, and with the right sensor arrangement, can even identify the location of the crack itself. So we can, with multiple sensors, can map the location that we are hearing cracks from and develop these three-dimensional charts of where the crack is occurring. So we can target the inspection team to go in and inspect specific components of the bridge itself. I mentioned integrating traffic cameras. This is a very common sensor that we will integrate. We've used a variety of different types, and we have a couple that we will use often, and they're typically the ITS cameras that most people are familiar with. We tie this to our monitoring system and we control the camera so that we're capturing images related to events on the structure itself, and of course present that alongside the data that we're collecting. When it comes to data management and visualization, again, we of course are trying to present the data in a meaningful way, but not only that, but to have a very secure portal for our clients to be able to log in, manage, and review the data they're collecting, as well as setting up alerts that they're concerned about particular sensors. Our system is all hosted on Microsoft Azure. It's a very high level of security. We have 24/7 phone support as well for any issues that our clients are having reviewing the data. So it's really a scalable program, a scalable platform for us to deploy on many different structures, as well as very large scale structures with very large data volumes. This is a snapshot of one of our projects in Arizona here. We've got a few bridges that we've instrumented and are presenting all of this data on this secure website. It's typically where we'll have some type of picture or rendering of the structure. We'll have the instrumentation plans integrated into the view, as well as rough locations of where sensors are located in the structure. So it's very easy to get a snapshot of the condition of the sensor, as well as drill down into the individual sensors and look at the data history for the last day, the last month, the last year. This project also includes cameras on site. So like I've been mentioning, we can look at an event and go directly to the image and look at the type of truck that was crossing the structure that created that event. Again, I mentioned a little bit about managing the monitoring systems. I think this is an area that is overlooked by most systems that are deployed, and really overlooked by a lot of the owners of structures. It's extremely important to have a monitoring system to evaluate the performance of your structure, but it's equally as important to understand how your monitoring system is behaving and the health of the system itself. So having a contract in place so that you can maintain these systems, you can evaluate the condition of the health of the system, really the power or the communication protocols that are being used are really important, really as important as collecting the data itself. So I can't really stress that enough. It's one of the areas that we've pushed a lot on our contracts in the US here, is to really make sure that the owners have a mechanism to maintain these systems. While a lot of the hardware available now is very robust, very reliable, it still requires some maintenance, and to have a mechanism to maintain these is very important. One of the areas that we've been involved with a lot now is these hybrid systems, where we have a monitoring system for the structure that's permanent, but we also want to look at a load test for the structure. So we've had projects where we've, again, installed a semi-permanent system and then come out and added additional equipment for a snapshot diagnostic test of the structure. And then it would roll back into a permanent monitoring system. So that's a very sort of typical process now, and have quite a few projects that we're involved with that involve that. So that rounds out my presentation to you guys here. I think we have about 15 minutes or so left. So I see that there was a whole lot of questions online, which I absolutely appreciate. I don't know that I can read almost any of them. So I will ask Zelfriki to step in. And if somebody has some specific questions, I'll be happy to jump back to any of the slides and discuss some of those in a little bit more detail.
Yes, thank you for your presentation, Jess. There is a good question now. I see in the question chat. It is a question from Mr. Luhur Subekti ST. Whether is it possible to do the dynamic test without stop the transportation, without stop the operation of the bridge?
Yes, yeah, that is possible, and we have done several dynamic tests like that, where it depends a little bit on the structure and the stiffness of the structure itself. So larger structures that tend to vibrate more, we've been able to use just ambient traffic to collect the vibration of the structure and then calculate the frequency of vibration of the structure. So yes, it is possible, but again, highly dependent on the stiffness of the structure itself.
Oke, jadi jawabannya Pak Luhur Subekti, apakah pengukuran dapat dilakukan secara dinamis tanpa perlu memberhentikan kendaraan terlebih dahulu? Jawabannya bisa ya Pak, dengan metode ambient vibration test. Okay, maybe you can also see some question in English. You can choose.
Sure. Let me see here. I'll skip through. I'll try and find one here. I
Silakan
see
yang
one
mau
on
bertanya.
whether
Yang bertanya.
the testing software for steel structure is the same as finite element. Let's see, same as, let me open up this question here.
There is a question, Jess, maybe about the question of the software, yeah, for calculating the steel, yeah.
Yeah, and then for the finite element analysis software, it really does not matter the material type of the structure. So most finite element analysis packages will have the ability to define the material that's used in the different elements. So it does not matter for us. I think the more complicated analysis is typically concrete because it's not a homogeneous material. So we have some steel, we have some large aggregate. We have to come up with a effective modulus that includes the reinforcing steel within the concrete.
Oke, mudah-mudahan jelas ya Pak. Ini elemen software itu, elemen analisis itu tidak hanya terkait dengan steel, bisa di baja, bisa di beton, bisa material apa aja. Bahkan ini elemen analisis itu juga bisa memodelkan tanah, ya, soil interaction dengan struktur atau join per join gitu, dan bisa digunakan hampir di semua bidang ilmu ya. Sekarang finite elemen analisis itu digunakan karena penelitian dengan finite elemen analisis itu jadinya jadi lebih murah gitu ya. Okay, Jess, you can choose the other question maybe.
Yeah.
I would like to ask you to answer one question. There is a question from Miss Dina Cahyadi. Can we do the test to do the test to the bridge that is built? As the build, and after the building the bridge, they don't do load test, like acceptance test.
Yeah. So is it possible to do load test after building? Yes,
but after the test, after the building, they don't do that. But yeah, they use without acceptance test.
Yeah.
The existing.
We've conducted quite a few tests after construction, and even if they don't do a test right after construction, of course you can do a test at any time and evaluate, you know, really the performance of the bridge at that time. I know in a lot of places we look at doing load tests right after construction to evaluate the performance as it was constructed. So basically verifying that it meets the design criteria of the structure itself.
Okay.
I see a question here about what is the method for best evaluating fatigue life on bridge structures, and which instrument can we implement? And I think that's a good question.
Who has a question? The name?
I think it's a Widi Nagruha, if I'm saying that correctly.
Widi Nugraha. Okay.
So I think that it's a good question because I get asked that question quite often, and the answer is not so simple because we don't know. Typically, we don't know the history of the bridge. So when we look at the fatigue life, it's going to be very difficult to evaluate the remaining fatigue life without knowing the loading history. But what we can do is we can install sensors in critical locations to look at the stress levels. And typically then we collect data over a period of time that is maybe representative of a typical, you know, week or month, and evaluate the stress cycles and the number of stress cycles at those different levels. And so we can see how often we're getting stress cycles at critical levels, and to see if maybe it's not in a fatigue state, meaning that we don't have any cycles high enough to potentially register the fatigue life.
But yes, I ever read in the paper to know the fatigue life of the bridge. If we has the long historic, the big data, we have the big data of the bridge,
Yep.
and we also has the model finite element that is updated, validated. It can be calculated, but it needs a statistical analytic. Yeah?
Yes.
Not easy.
No, it's not easy. You're right. But if you
Not
have
easy.
if you have that data, you can make a very good estimate of what that remaining fatigue life is.
Yeah.
For
But
rail
it is possible.
bridges, it's really much more possible on a rail bridge because you know, depending on how good the records are, but they're much better than highway bridges. So
Yes.
typically we know the number of vehicles that have crossed that bridge, and so we can dig up that history and come up with a more accurate fatigue life of the bridge.
Yes, but it is possible.
Yeah, yeah.
Yeah, it is possible. Okay.
It is possible, just difficult.
Yeah, not easy. It needs many people, not only one people. Yeah, because it calculate many data, like statistical data.
Yeah.
The next question is from Miss Fatma Yusrizal. It is one of Ibu Dina as bridge consultant, the famous bridge consultant company here. Miss Ibu Dina has a staff, Miss Fatma Yusrizal. He has a question. I think his question is, what are pros and cons for old style strand gauge versus transducer? Maybe precision or something. Yes, maybe you
Yes,
can
yes.
answer this.
Yeah, it's a very good question. There certainly are pros and cons. So we use both on many projects, and it depends on, again, those pros and cons. So for strain transducers, we typically only use those for short-term diagnostic tests, like a live load test, because our strain transducers are not well compensated for temperature and are sensitive to temperature. So they're typically used, again, for those diagnostic load tests. If we are looking at a long-term, like a structural health monitoring project, then we typically use the more traditional strain gauges, which are compensated for the material type that they're installed on. And we use those with bridge completion modules that are also compensated. So they're just a more they're better for temperature compensatable applications, long-term monitoring.
Jess, you may answer my question, Jess.
Yes.
Would you like to explain more in geotechnical instrumentation? Geotechnical instrumentation. If you have some cases or measurement, so please present.
Yeah, let's see if I can go back to one of this geotechnical slide, because it's one of the areas that we do some geotechnical monitoring, but we don't do a lot. Our focus is mostly on the structure.
Oh yeah.
That's where our main focus is, but we do often have to integrate geotechnical instrumentation as well, because it's part of the whole package of instrumentation. So if there's components around the structure where geotechnical issues may impact the structure themselves, or if it's just purely a geotechnical instrumentation project, we can certainly deploy sensors that would look at slope stability, look at the changing of a slope as time or water pressure increases. Like we've got here, ground. Pardon me?
Inclinometer as well.
Yes, inclinometers. Yep, inclinometers in the ground. We have a project in Colombia that is looking at just that. It's looking at critical land formations around their bridges that are susceptible to landslides. So we will be installing inclinometers, accelerometers in the ground, and piezometers to look at how this ground slope is possibly moving with either earthquakes or with water pressure. Some of the larger scale bridge monitoring projects will also include some geotechnical instrumentation, but for the most part, our work is focused on the superstructure.
Okay, there's a question also. Next question. How is the frequently to do the inspection of the bridge with this tool? This is from Mr. Agus Setiawan.
So could you repeat the question?
How frequently we should do bridge test with load test?
That's a difficult question, I guess. For us in the US here, it varies. So mostly we will conduct another load test when the condition has changed. That's the visual or the inspected condition of the bridge. For the other load tests that we're involved with, if the condition hasn't changed, then the load test and the load test results are typically accurate. So in that case, really you have to rely on your inspection program as well to let you know that you think something's changed and you're not sure whether those results are valid anymore. That may trigger another load test.
Okay. Thank you for your question. You answer. Yeah, there is a question also from Mr. Widi Nugraha again. Mr. Widi Nugraha tell that he's interested with the wireless sensor.
Mm-hmm.
And in wireless sensor, he faced a lot of problem with noise and low reliability compared to the cable system. How about the BDI wireless system?
You know,
what is the problem with BDI? Also similar with the other system?
Yeah, for our diagnostic testing system, we've spent a lot of design time in reducing noise in these systems themselves. We've had probably a wireless system for about 15 years now, and have been using it successfully on many different projects. There is always a potential for interference, depending on the wireless technology that's being used, and depending on the design of the hardware. You have to design it to be immune from electromagnetic interference, and you have to design it to be, somewhat self-healing with regards to communication and data transmitting. So I've heard the same thing from many different systems, and depending on where they're deployed, the reliability can be questionable, and the battery life can also be questionable. So it's for long-term health monitoring, it's going to be very difficult to find a true wireless system for long-term that would be economical against hardwiring a system. But for diagnostic testing, we've been very successful at developing our hardware and then our sensors with the correct kind of shielded wire to reduce noise and signal impedance from the data that we're collecting.
Okay, thank you for your answer.
Mm-hmm.
Also, there's a question about wait a moment. I just interested also with his question about the Hi, but acoustic emission maybe. Could you explain again the principle of acoustic emission? Miss Eva Suryani is asking for acoustic emission.
Yeah.
How is the principle? How can they can get the data?
Sure. I was just going to go back to one of the slides here that sort of shows the acoustic emission. So acoustic emission is a sensor that's listening. It's really an ultrasonic receiving sensor. It's listening for noise or impacts that travel down the structure itself. So it's a very, very small, we can sort of see one right here installed on the steel. This is an acoustic emission receiver. And so when a crack occurs or an impact on the structure itself occurs, it sends a signal down the steel or down through the concrete or through the wires, and we can detect that signal. When it comes to steel, it's a very specific acoustic signal that travels through the steel itself, and that's calibrated. So when a wire breaks or steel cracks, it's a very specific acoustic signal that is recorded by the sensor and the data acquisition. And with multiple sensors in different locations, the time at which that signal arrives to the sensor can be correlated between multiple sensors, and we can triangulate back to where that sensor or where that signal came from, so where the crack actually occurred. And it's very useful on tendons where we have individual wires that can eventually break from corrosion. We can hear that very distinctly on those cables.
So this is actually ultrasonic method, yeah, but online monitoring.
Yep.
Oke, ya mungkin Ibu yang bertanya acoustic emission ini ultrasonik, metode ultrasonik. Nanti siang juga kita ada webinar terkait ultrasonik tapi aplikasi di beton. Memang ultrasonik ini bisa menampilkan 3 dimensi di dalam material, apakah itu beton atau baja atau material lain ya, dan bentuk cacatnya, posisinya, besarnya, ukurannya, letaknya dengan spesifik bisa kita lihat. Nah itulah kira-kira acoustic emission gambarannya. Kalau mau join silahkan kontak WA saya, nanti ada webinar jam 2 terkait aplikasi acoustic emission ini. Okay, you can choose also what you can answer.
Yeah. Well, I think we've exhausted most of the English questions here.
Yes.
I see one here which tell me a little bit more about realistic load test utilizing weigh in motion. We have some weigh in motion sites, and it is interesting to utilize WIM for loading test. What is the limitations and how is it compared to static loading test? So that's a good question. We would, of course, we would not install a weigh in motion for a diagnostic load test because it's too costly. But what we're typically using them for is looking at the types of vehicles that are crossing a structure. So we're able to classify the vehicle types and look at the axle weights. And then when we collect data from a monitoring system, usually we're setting up the system to be able to capture event data. And that means we have a threshold of strain or displacement or rotation, something that would trigger the system to capture data before an event and then after an event. And if that event is causing some large stress, we can go back and look at the weigh in motion data to tell us the type of truck that was crossing the bridge. So we might find that a certain truck configuration causes the bridge to vibrate more and amplifying the stresses than maybe say another truck configuration. So hopefully that helps answer that question.
Okay. There's a question, maybe still similar question, but maybe you can answer with a different way, maybe. From Dr. Andes Agus Harno Nurdin Shah, Master Science, whether there is whether any possibility to understand the age of the structure related with fatigue, yeah, of the building.
The age, as in how, like, maybe when the structure was built?
Yes, the age related with fatigue, yeah, material fatigue.
Material property, yeah. Yes, there's ways to do that, but typically that is not done through load testing or monitoring. That gets into non-destructive evaluation methods. So we would look at scanning concrete with different tools that might help us evaluate whether there's corrosion at the level of steel, or even potentially drilling cores in the concrete and sending them to a lab to evaluate the strength or chloride content, things like that. But not so much a diagnostic test or a monitoring system would be able to identify the age or the material properties directly.
Okay. There's a question from Mr. Samuel Nengolan, whether these instruments are compatible for railway bridge.
Yeah, of course they are. We've done many projects on railways, and so the application is really identical for railways as it is for highway bridges.
Okay. There is a question from Muhammad Habibi, how to do load test for the maybe not too long bridge, short span bridge, like railway bridge.
Yeah, well, that goes to similar to that example I showed from the case study of the bridge in Arizona. So you can see this is a relatively short span bridge, and most of the diagnostic tests that we conduct are on short span bridges. So there's really no difference. We just want to develop an instrumentation plan to collect data that would help us evaluate the load carrying capacity of the bridge. Very similar to what we did on this structure here. And then again, the same thing would apply for a railroad bridge.
Okay. There is also next question from Dr. Andes Agus Harno Nurdin Shah, Master Science. How long we can understand that one building is having a problem, or maybe can be fail with instrumentation?
How can we understand, or how long till we understand?
Maybe he want to know how is the procedure to understand the behavior of the building. Maybe it will be failure, or maybe it will be fail. Maybe sometimes how long they get understand that with having instrumentation.
Well, it's a good question, and you know, there's maybe not a direct answer, because we have to think about diagnostic testing or structural monitoring as a tool. This is a tool for us engineers and the owners to make better decisions, informed decisions on. So there's not going to be very many tools that will tell you when a structure is going to fail. If there's some level of near failure, like the bridge is going to be falling down, we will detect you know, changes in the structure that would lead us to say, you know what, we have a problem, we need to close this bridge, or it's failing. but it still involves the engineer evaluating the data and making a decision. So there's not going to be anything that'll tell you directly this bridge is going to fail or this building will fail in 1 year. There's really nothing that'll do that. It's the engineer and the analytics behind it that will help evaluate that.
Yes, so this is only the tool, and you have to analyze the data.
Yes.
Yes. From Mr. Hari Triwibowo, so he said that each instrument must be calibrated routinely. How about this data logger and each sensor?
How frequently to calibrate?
Yes. Also, he would like to know what parameter must be calibrated related with data logger.
The data logger itself is calibrated at the factory, when we produce it, and doesn't need to be calibrated over and over again. We're calibrating the system to the electronic components as they were produced, and it's very, very, very minor adjustments that are made. And we've calibrated our systems for years and years, and those calibration constants don't change in the data logger themselves. The sensors for permanently installed systems typically never need to be calibrated again. It depends a little bit on, of course, the sensor manufacturer, but most of our sensors will not require to be calibrated. The only time they really need to be calibrated is when they're used over and over and over again. So for our diagnostic testing system, where the strain gauges are being installed and then removed and then shipped to another bridge and then installed and removed and shipped and so on and so forth, we recommend those being calibrated every couple years. And the history of us doing that, they really don't change very much. It's really only when somebody bends the gauge or pulls it out of its range that it really needs to be calibrated.
Okay. There is a good question also from Mr. Bagus Subandono. How to know the remaining strength of the structure material in the bridge, mainly in the girder.
In the girder, yeah, that's a good one. It's difficult. Concrete is very difficult to do. I don't think there is a direct way to do concrete without drilling a core in the concrete. For steel, there is some ways. We have, and I actually did this testing for the Department of Public Works in Indonesia, where there's a method for drilling a very small hole in the steel and measuring the release of stress around that hole. And what that tells you is the residual stress in the girder at that location. So knowing what the in situ residual stress is gives you the remaining allowable stress before failure. So that's one method that can be utilized for steel.
Okay, so it is like a non-destructive testing method.
Yeah.
It is using what's the name? Nuclear or
no? It's called the residual stress method, and yeah, and I believe that the Department of Public Works there they own one of these systems.
Okay. There is many questions. Yes.
Yeah, well, I know we have many questions, so I don't think we have time to go through all of the questions here because we're we're a little bit long. But what we can do is we can download all of these questions, and,
yes.
and then Selfreaky, if you want to translate them for me, I can answer all of the questions, and we can get those answers back to everybody that posted questions here.
Yeah, I think I also I say sorry to all of you that have sent us the questions. This session is really not enough.
Yeah.
But we and BDI will be happy to have a special next session with you and your organization, maybe your engineering team, if you like us to discuss with you your projects or your problems. And I will invite Jess. We will have a special discussion about your projects. Maybe you can contact me. Setiap orang bisa kontak saya, and I will invite Jess. So maybe we will discuss more details, yeah, because the session is only 1 hour and 30 minutes and already past the time.
Yes, well, I think I'm very encouraged to see all of the questions and appreciate everyone taking the time to listen to the presentation here. And I think your idea of having a follow-up with maybe some more direct discussion on projects and questions people have is a great idea. So I look forward to doing that. We have this presentation being recorded, so we will share that with Zulfriki, and we'll make sure that that's available for you guys. And there was also some handouts that hopefully you guys were able to download on the side of the presentation here. And I'll also make this PowerPoint available for everybody to download as well. So I guess I'd like to thank you again for taking the time to listen here, and you know, look forward to meeting with you guys sometime in the future here and talking again.
Ya, Bapak-bapak dan Ibu-ibu yang kami hormati, sesi ini memang tidak panjang, tapi kami dari BDI dan Testindo, kami siap untuk kita buat sesi khusus jika ada proyek atau presentasi khusus di perusahaannya atau di lembaganya. Silahkan kontak Bu Fikri, saya akan undang Jess nanti. Kita bisa lanjutkan sesi khusus mungkin ya, karena waktunya telah habis. The session is end, I think, Jess ya. And Jess also will send me the question list by email. Also the recording and PowerPoint, everything will be available. The video you can see in our YouTube channel, Testindo YouTube channel. You can see and download from YouTube. Also, the material will be put there also in the description. You can get everything from this session, and I hope all of you get the benefits from this webinar. I'm sure Jess also would like you to learn a lot from this webinar. Okay, Jess.
Okay, well, thanks again to everybody, and I'll sign off here since it's late here for me, and I hope you guys all have a great rest of your day, and we'll be back in touch shortly.
Okay, thank you for your time, Jess.
Yes.
Also, all BDI family there. Terima kasih juga kepada bapak-bapak, ibu-ibu semua komunitas sipil engineering Indonesia yang meluangkan waktunya kepada PU Organisasi, bapak kita yang terhormat, mudah-mudahan sehat-sehat selalu. Semuanya juga terima kasih telah hadir di join session webinar kita pagi ini. Oh ya, yang ingin join session webinar siang ini jam 2 kita ada webinar NDT for concrete. Yes, we have also another session of webinar this afternoon at 2 p.m.
Oh, you do? Okay.
Yeah, everyone can join. Also contact Zulfikri di nomor WhatsApp saya. Silahkan yang mau join webinar siang jam 2 tentang ultrasonik untuk konkret. Ini juga terkait dengan acoustic emission tadi yang tadi kontak WA saya akan share ke Anda Zoom linknya untuk join webinar jam 2 dengan pembicara dari Jerman dan juga expert di bidang acoustic emission ini. Oke. Thank you for all of you. Thank you very much.
Okay, well, thank you, everybody. Goodbye.
Goodbye. Bye-bye.
Bye. See you, Jess.
Bye.